All right, welcome to class again. This class period is for Wednesday, March 25th, and this is chapter 12, starting the next section here before test 4, coming up at the end of the semester. Reminder, quiz 7 is due tonight online. Make sure you upload that before midnight. And this is also the last day of test 3. Remember, test 3 goes over Tuesday and Wednesday. Make sure you take that, see the PDF there, fill out your answer sheet, and upload that to Learning Suite by tonight. Tonight is the last day on that. Chapter 12 involves oxidation reduction reactions. So we'll mainly be looking at the reduction of alkenes to alkanes, actually this type of reaction here. Taking the pi bond and converting it to an alkane, that's a reduction reaction. We'll also be talking about oxidation reactions. So if we add oxygen here, make an epoxide from an alkene, or make a diol from an alkene, going to the right here on the top is an oxidation type process. We're adding oxygen. Now, when we talk about oxidation reduction reactions, we're talking about a progression of functional groups. We've already seen all these groups, and you can think about these conceptually from left to right as undergoing an oxidation toward the right or a reduction to the left. Okay, so in this chapter we're kind of going both ways. This first lecture today will be mainly reduction reactions. There'll be a few new ones there that we'll need to talk about, but we're familiar with the functional groups, so that should be okay. Oxidation, if you look at this progression here from ethane to ethanol, what we're adding an oxygen between a carbon-hydrogen bond. So it's definitely an oxidation, dramatically changing the properties of this compound. And then we can also think about taking away 2 hydrogens there and making an aldehyde. So that's also what? An oxidation reaction. What's also an oxidation from the aldehyde is if we add in another oxygen and make the carboxylic acid. Okay, so definitely an oxidation. And then the ultimate oxidation always is ending up at carbon dioxide. That's the most stable form of carbon there is. It's a gas molecule, makes up a small percentage of the atmosphere, right? So CO2, by the way, that's where we all end up. We eventually all oxidize and end up with this thermodynamic stable product, CO2. And also you can think about that as the combustion product. Yeah, all organic compounds burn, they combine with oxygen, and with enough heat, a spark, whatever, end up at CO2 and water, okay? So that process you can see there. Now in biology, and why we're talking about this, why are oxidations and reductions important? Well, in biology, we've got metabolism, right? Converting glucose first into pyruvate, one glucose molecules converted into 2 pyruvates, and then ultimately onto carbon dioxide and water. So that metabolism reaction. And it is net exothermic, gives off heat, and accounts for a lot of things in biology. So the reactions we're going to be covering are paradigms for this biological process, and it shows you new ways to interconvert organic compounds. So if we can go back up to the chapter outline here, and look through the reactions we're going to be covering, and I'll try to point out exactly, which ones are new. A lot of them are kind of similar to what we've been talking about, but we'll talk about specifically what oxidation and reduction means. We'll define that very carefully. First, we'll look at reducing agents, things that can donate hydrogens or electrons or hydrides. So we'll go over the basic type of reagents that we'll be using for reductions. For alkene reduction, we'll talk about hydrogenation reaction with hydrogen gas and a palladium, platinum, or nickel catalyst. Mainly for this class, we'll just show PD for palladium. But if you leave out that palladium, then there's no reaction between hydrogen and an alkene. You have to have that catalyst there. You see, you go from an alkene to an alkane. Now that's just adding hydrogen across the pi bond. We'll also talk about carbonyl reduction. Ketones or aldehydes can also be reduced. But remember last time we said carbon-oxygen double bonds are more stable. So it takes more time and a more active catalyst to actually get this to go. And when you add hydrogen across a carbonyl, a ketone or an aldehyde, you get an alcohol. So a different type of product, but very similar reaction there. So that I would say is reaction 1 we need to keep track of. We'll talk about an application here, hydrogenation of fats, polyunsaturated fats to go to unsaturated fats, and then ultimately if you keep hydrogenating onto the saturated fat, okay, from the oils to the solid Lars there. And the cis-trans issue comes up again there in a couple spots. Now, reaction number 2 is alkyne reduction. We can reduce both pi bonds with excess hydrogen and palladium to go from an alkyne to an alkane, or we can use a poison catalyst, we call it. This is a so-called Linlar catalyst that has palladium with calcium carbonate and added lead tetraacetate. Pb is lead, plumbium from the Latin, if you remember how that is named there. Lead, the symbol's not L, it's Pb, okay, for plumbium. And if you have that lead acetate there, we say that's poison catalyst there. This is a real witch's brew. Sometimes there's quinoline in there, which is a heterocyclic complex compound that also coordinates the palladium and attenuates its reactivity. So it only does the half reduction from the alkyne to the cis-alkene. That's the key thing there. And if you want the trans-alkene here, you use sodium metal and ammonia. You go from the alkyne into the trans-alkene. So that's the third reaction. And we'll also talk about reduction of alkyl halides with lithium aluminum hydride to go from a haloalkane to the alkane reduction process. And we can also open up epoxides to alcohols with lithium aluminum hydride. We'll show you what that reagent looks like and everything there. Now that's today, we'll just do the reductions. Looking forward to the oxidations. Next time, we'll talk about oxidizing alkenes to epoxides and to diols. And let's look at the new reactions there coming up just briefly. And we'll summarize these and go through these, like I said, next time. We'll have alkene epoxidation, which is you have a cis-alkene, we'll go to the cis-epoxide. If you have the trans-alkene, it will go to the trans-epoxide using a per acid, MCPPA for metachloroperbenzoic acid. Here's a per acid. It has a peroxy group in it. So it has the carbonyl and then 2 oxygens here, and then the hydrogen. Okay, so that's what we call per acid. We'll go over the mechanism and the stereospecificity of that reaction and talk about that. We'll also talk about dihydroxylation of alkenes, either from the epoxide, if we open that up with hydroxide base, we can get the trans diol here, the di-alcohol compound from this cyclohexene oxide epoxide here. Or we can go directly from cyclohexene and do a dihydroxylation with osmium tetroxide to form the cis-diol product. CHEM351 also does this. We'll also talk about that. But those are new reactions, epoxidation and dihydroxylation with osmium. And then we'll also talk about cleaving both the pi bond and the sigma bond with a very aggressive reagent. Maybe you've heard about it before, ozone, O3. This converts an alkene to the carbonyls on both sides. So this alkene, for example, this 2-methyl-2-butene is converted into acetone and acetaldehyde by cleaving right here, both the pi bond and the sigma bond with ozone. We'll do a little bit on the mechanism, not much. You'll see how it works. We call that molecular scissors that can cleave both the lower energy pi bond and the higher energy, the more stable sigma bond. Go to that. Yeah, cleavage also of alkynes. Those generally go into carboxylic acids. We'll say a little bit about that. Then the last reaction, sorry, there's a couple here, right? Alcohols can be oxidized, like we said, to aldehydes or carboxylic acids if they're primary. If it's a secondary alcohol, it can be oxidized to a ketone. And we'll have a new reagent here, pyridinium chlorochromate, or PCC, which oxidizes a primary alcohol, and it stops at the aldehyde, okay? We'll have a little added application here, the breathalyzer test. Maybe you've heard about that. a law enforcement issue to estimate blood alcohol content in DUI people, but that will be a colorimetric change from chromium in the higher oxidation state, which is red, and in the breathalyzer tube, if there's ethanol in your breath, the chromium will change from red to green, and that's a consequence of the chromium getting reduced. Anyway, say more about that next time, and we'll do an asymmetric epoxidation, ethanol oxidation. Oh, and we'll show the version in nature too. Nature's oxidizing agent is NAD+. You've probably heard about that cofactor, and we'll say more about that. All right, let's look at the reactions here more in general and define exactly what oxidation and reduction mean. So you've heard about oxidation and reduction in general chemistry, probably talking about metals. And we talk about metals in their elemental form, their shiny form, silver, for example, or gold or copper. In their reduced form, they have zero charge, and they're metallic materials, ductile materials, whatever. They have a melting point that's very high, whatever. But they can also be oxidized. So like iron, for example, reduced iron is the shiny iron stuff, but it readily oxidizes to the red material, which is iron oxide. So those kind of things we're kind of familiar with. But oxidation in OChem means removing hydrogen, okay? So taking hydrogen away or adding oxygen. Okay, now the Gen Chem term for oxidation is what? Removing electrons and going to a higher oxidation state, higher charge on the metal. So we'll add that in, taking electrons off. So it's really three things here, but in OChem, looking at the functional groups, it's mainly taking away hydrogen and or adding oxygen is what we mean when we talk about oxidation. Now, reduction means just the opposite. We're talking about adding hydrogen or adding oxygen, okay?
Removing oxygen?
What's that? Oh, or taking away oxygen, thank you.
Yeah.
Good thing Isaac's here, okay. Yeah, reduction, we're gonna add hydrogen, which is the opposite of oxidation, right? And taking away oxygen, instead of adding it here, we're doing reduction. And what would it mean from an electron point of view? Well, we're adding electrons and going to a lower oxidation state. So let's see here in OChem, how about this? If we have an alkane and we go to an alkene, what are we doing here? We're taking away two hydrogens. So what are we doing? We're actually doing an oxidation here. We're taking away two hydrogens. And we can take this a step further, right? And go to the alkyne here, okay? Let's look at the Gen Chem example here with metals. Maybe do the example with sodium chloride. And sodium in its elemental form would look like this, right? So it's first row element there, it's got one valence electron, and that's it. And let's look at chlorine, elemental chlorine. We have what? 7 valence electrons. It's right on the edge there next to the noble gases. So what do we do here? Sodium will give up this electron. Notice I'm drawing a single fishhook arrow there. That's part of the mechanism here. Sodium is what? It's got no charge on it, as well as the elemental chlorine has 0 charge on it. And when we transfer this electron, what happens? We go to sodium plus, okay? We said it's in a higher oxidation state. We went from the 0 oxidation state to the +1. And then elemental chlorine, what? Added an extra electron, so what is it now? It's got the 8 electrons around it, so its charge is -1. It got what? Reduced, okay? And we say the sodium got oxidized, okay? And both of them now have the electron configuration but the noble gases. So these terms are probably more familiar to you. Let's look at the different reducing agents now that we're going to use here in this chapter. and these different reagents and what they do just conceptually. So the first thing is hydrogen gas, but on its own, it's not able to react with an alkene or alkyne. We need to have it also in the presence of a catalyst, palladium, platinum, or nickel, whatever. Those two things together have the potential to deliver the hydrogen atom and reduce an alkene or an alkyne. So the actual thing that does the reduction then will be a palladium hydride. We'll go over the mechanism a little bit for that. Maybe not too much, but you can see there, this is going to be a hydrogen-rich reagent. It's going to have the potential to add that to the substrate. The other ones we're going to see, sodium metal and ammonia. The ammonia is just the solvent and the proton source. The sodium metal is going to be the reducing source. You can see the free electron. This will be the elemental sodium. This will be a very vigorous reaction. We'll be doing the reductions of alkynes to transalkenes with sodium and ammonia, but that's the type of reagent there. Another ones we're going to look at are sodium boryl hydride and lithium aluminum hydride. Now when we say hydride reagents, what are we talking about? We're talking about H with 2 electrons and a negative charge. Now there's no negatively charged hydrogen floating around here on these reagents, but let's look at the details of this reagent. So this would be sodium, metal, and then what is the boron? Boron has what? 4 hydrogens on it. And what would be the charge of boron with 4 bonds? Remember, boron only has 3 valence electrons. So this 4th bond makes us what? Right, negatively charged, okay? So if you draw out the ionic version of this reagent, you see the potential to transfer a hydrogen with its pair of electrons to give the neutral borane, okay? So that is the reduction source. Same thing with lithium aluminum hydride, lithium with aluminum and 4 hydrogens on it. Aluminum is right below boron in the periodic table. It's the next row down. So it has the 3 valence electrons. The 4th bond here will make it negatively charged. And that will also have the potential to do different reductions. We'll see the reduction of alkyl halides and the addition to epoxides with the hydride adding there. So those 2 reagents are important there. In nature, it's a little bit different. The main reducing reagent there, cofactor, maybe you've heard, is NADH. Stands for what? Nicotinamide adenosine hydride. Okay. Where is the hydride? Well, the nicotinamide group looks like this. I'm not going to draw out the whole cofactor, but the nicotinamide has an amide functional group. That doesn't participate in the reaction. What will actually do the reduction is the motion of the pair of electrons here on the dihydropyridine, and then there is where your H plus minus can come off and do reduction. So NADH will be Mother Nature's reducing agent. If we got time, I can show you how some of that goes about. But it's completely analogous to the hydride being able to come off boryl hydride or lithium aluminum hydride in a reactive sense. All right, let's go to the alkene reductions here and see what we're going to look at. I'll draw some results here from alkene hydrogenation. So this is hydrogenation, our first reaction we need to look at. And we'll look at alkenes in the presence of hydrogen gas with this palladium or platinum catalyst. And you don't need to say cat or whatever. Just show the palladium and show the hydrogen here. And the product will be what? The alkane. So alkene to alkane, and we're just reacting with the pi bond. Do we have a feel for how exothermic or endothermic this process might be? Well, we can already see what we're doing here. We're breaking a pi bond, which is about 60 or so kcals per mole. Yeah, we've got to break a hydrogen-hydrogen bond. That's a little over 100 kcals. That's tough, but that's what the catalyst is there for, actually. And then look, we're making carbon-hydrogen bonds, and they're both worth quite a bit. They're 90 or so kcals per mole. So 90 kind of added up, 160. So you can already see, and maybe we'll do the math here in a second to see what's going on. But let's look at some specific reactions first. So here's one pentene, hydrogen, palladium. That combination goes to the alkane. Okay. So let's see. If we have two pentene, trans 2-pentene, same thing. Oh my God, it also goes to pentene. Okay, so it's not too much of a deal there. But if we have a cis, oh yeah, also the same thing. Okay, same product there. One other observation here to look at first before we examine the mechanism. Let's have some more substitute alkenes. And when we have a more substituted alkene, these actually react faster. These have faster rates. These are more electron-rich alkenes due to the donation, the electron density there. And notice that will also give the alkane product. You keep the carbon framework exactly the same and just put hydrogen across there conceptually. Let's see another example. Here, if we have an alkene with 4 carbons on it, a tetrasubstitute alkene, and it's cyclic here, now we can track what? The stereochemistry. Where do the 2 methyl groups end up? Do they end up cis or trans to each other, the product? And this is kind of an indication of the mechanism. Let's see. It ends up, yep, you're right, it ends up cis. So it's 2 hydrogens, what? Come in on the same face of the alkene and give the cis product there. One other thing to look at. Let's look at the energies of this reaction. And we're going to look at the mechanism, of course. Let's look at the energies of this pentene series. So here's our energy. Here's our reaction progressing here. And we've got 1 pentene. And this will go downhill to pentane. Okay. And we've also got cis pentene. And we've got trans pentene. Now I'm just going to do a series with just 3 in there, but we have what, a terminal alkene, monosubstitute. Here we have a disubstitute alkene, which is cis, and here we have a trans substitute alkene. And we've talked about the relative stabilities of alkenes. The more substituted, the more stable they are. When all of these hydrogenate, they all give off heat associated with them, and they all go to the same product here. Okay, so there would be the change in energy going from the alkene to the alkane. Already mentioned it's exothermic, but exothermic by how much? So these all have different starting points. Okay, so there would be less energy coming out for the disubstitute alkene, and then we have the trans one here, which is a little more stable still. It goes to the same product here. How much heat of hydrogenation? Okay, we can measure this heat quite easily experimentally in a bomb calorimeter and see how much heat we're actually getting out. Well, if we hydrogenate this pentene here, we get out minus 30 kcals. Okay, when it goes from the 1 pentene down to pentane, minus 30 kcals per mole. Okay. How about if we hydrogenate the cis 2-pentene, we get out minus 28. A little bit less. Okay, why is that less again? Well, we're starting at a little bit lower heat of formation position, right? This is more stable because it's disubstitute alkene versus a monosubstitute alkene, okay? But this one's cis, and then when we hydrogenate the trans 2-pentene, we get out minus 27. And again, that's very close, but you can see we get out a little less energy from the trans as opposed to the cis. And that fits in with our stabilities we've talked about. If the 2 groups are trans from each other sterically, they're apart from each other. So this molecule is a little more stable. It's a little lower energy, set point wise. And if we cis here, we have the two alkyl groups closer to each other, and it's a little less stable. But the heat of hydrogenation is borne out there. You see the relative stabilities of there. So that can be an important thing to keep track of. Also, the more stable ones, if we had tri-substitute or tetra-substitute versions here, isomers, they would give off, well, they'd be going to different products, so we can't really make a good comparison there. But they will react more quickly because there's more electron donation into the alkene there. Yeah, I don't think we need to go through the bond dissociation energies there. They are exothermic, and you can see these exothermic energies, which we can also estimate these from what? Having the positive number here of about 64 kcals per mole, what we're breaking here. Breaking the hydrogen-hydrogen bond about 104 kcals. You can look up those bond dissociation energies in your book. There's an appendix in the back of your book that has all those details. And then each carbon-hydrogen bond that we're making here is worth about 100 kcals per mole. So when we add up those numbers, we get to this. But these reflect the relative stabilities of the alkenes there that I think is kind of important. Anyway, let's look at the mechanism. We have part of that up here. Let's see, let's get this other board down. And through the mechanism, we showed a little bit of what's going on here with this reducing agent. Let's see the rest of the story here and see what we need to know. Oh, remember I said hydrogen on its own with an alkene's unreacted. We have to react it with the catalyst. And the actual catalyst involves the production of a palladium hydride. So the palladium has electrons on it. This is in the reduced form of the palladium metal. It's usually supported on a charcoal or a carbon support. Sometimes we say palladium on carbon. You can weigh out or add in a very small amount of palladium. You don't need very much. Less than 1 mole % is needed here. But the hydrogen bond is actually broken by the palladium to form a palladium hydride. And notice that goes from palladium in the 0 oxidation state to palladium in what? The +2 oxidation state. If we think of those as hydrides being on the palladium. Yeah, don't worry about that. So some people just show the mechanism like this. And some books just show it this way, where the hydrogens come out and the electrons kind of go around like that. The pi bond electrons are broken. You make a new carbon-hydrogen bond there. That kind of accounts for this syn addition, where we have the 2 hydrogens added on the same face. If you can see it there, remember we had the cyclohexene with the 2 methyls on there. It gave the cis product. So the 2 hydrogens going on, and that's fine. That's not actually how it works. Initially, the palladium forms a complex with the alkene that kind of looks like this. And this interaction is the pi electrons with an empty orbital on palladium that looks like that. And then you can actually get a hydride to transfer over and a new carbon-palladium bond to form here. You get a palladium hydride, now alkyl group. The ethyl group ends up being on the palladium. And don't worry about that step, but this is still palladium 2, but now with a carbon palladium bond and still a palladium hydride bond. And we say that this is an insertion step. We insert the alkene into this palladium hydrogen bond. And then we have what's called a reductive elimination step, where we go back to the palladium 0 catalyst here. And at the same time, we grab this hydrogen here with the alkyl group to go what? To the reduced product. Okay? So here's our product again, the alkane, and we regenerate our palladium catalyst with that last step. It's okay if you want to think about this reaction this way, where the hydrogens are just delivered from the same face, but it's actually this. There's much more evidence for this now. But don't worry so much about the mechanism. Let's show you how we can use this reaction and what it's important for with hydrogenations in general. We have compound here with a couple double bonds. Maybe not, we're not sure what the structure is, but we've got this, which is what, C7H10. Now add up all your carbons there. I think there's 7, count them up. Hydrogens, remember we talked about what? The degree of unsaturation here. The maximum amount if we have 7 carbons would be what? 7 times 2 plus 2, which would be 16, right? But we don't have 16 hydrogens here, we have 10. So 16 minus 10, that's what, 6 divided by 2. So we have what, 3 degrees of unsaturation. And what do we mean by that, degrees of unsaturation? We mean we must have 3 alkenes, pi bonds, or 3 rings, or some combination, 2 rings, 1 double bond, or 2 rings, 1 double bond, or what? 1 ring, 2 double bonds, 2 rings, 1 double bond, or maybe 3 rings. Be a lot of options here. Well, let's go ahead, and if we have this molecule, and we do hydrogen with excess, and a lot of times it's always excess. It's really hard to measure out 1 equivalent hydrogen. So if you show hydrogen here, pretty much every alkene is going to get reduced. So for this case, it would go down to this product. Would not break open the ring, would just what? Hydrogenate or saturate the pi bonds. And then if we look at the molecular formula here, we see 7 still, H what? H14. And what? We still have 1 degree of unsaturation, right? So we must have what? 1 ring. So there's ways to use hydrogenation in combination with this analysis to kind of estimate what we're going to do there. And that'll be important for NMR and mass spec coming up. All right, what about other pi bonds? We also have carbonyl bonds. And carbonyls can be what? Aldehydes or ketones. So we have palladium there, or a ketone here, same thing. Can we reduce that pi bond, add hydrogen across there? Well, this is a carbon-oxygen double bond now. It's more stable. It actually takes longer time or heat or a better catalyst. Actually, a rhodium catalyst would do this better. But you can get what? The alcohol product here. And I'll show the 2 hydrogens, coming from the hydrogen gas there. But what this is just what? The primary alcohol, okay, from the aldehyde. A ketone, similar thing. Here we would stop our reduction at the secondary alcohol. So primaries from aldehydes or secondary alcohols. Can we do a tertiary alcohol from a carbonyl reduction? Let's see. No, we need, what, at least a hydrogen here to do that. So we can do secondary, you see from here. But looking at the structure of a tertiary alcohol, we can't make that from a hydrogenation. Why? Because there's no second hydrogen here. Okay, so mechanistically we're limited at that point. Let's look at a reaction here where we've got a combination of those functional groups, a carbonyl and an alkene. Let's do this. So we've got this ketone that has a long chain and then an alkene right here. Let's do the hydrogenation with palladium. Which one's going to go first? Well, it's going to react with the less stable one. That's going to have the lowest kinetic barrier associated with it. The more stable pi bond is going to be harder to get to that transition point. Like I said, more active catalyst. So if you just conduct this reaction for a short amount of time, what can you get here? You can get the alkane right there, and the ketone will still be there. Now, if you reacted this with more time or heat, okay, you could what? Reduce that also. So you could get the secondary alcohol right there, and of course the alkenes are already reduced. So you got some selectivity. You can selectively reduce an alkene in the presence of a carbonyl. All right, let's see. Let's look at, back up at the board here, some applications of this. Here's what we talked about, of course, looking at the different functional groups. going from alkanes, alcohols to carbonyls, and eventually on to carbon dioxide. So across the top is oxidation. Reduction is the other way, and that's what we've been talking about, an alkene to an alkane. Here we see the pi bond thing, so if we're, adding hydrogens here, we're talking about what? Reduction, yeah. So an alkyne, which we'll get to in a second, or the alkene, which we just did here. If we add 2 more hydrogens there, yeah, that's a reduction there. And we can think about this from in nature here. We talked about these unsaturated or double bonds in these long chain fatty acids. In nature, they often exist as esters, so don't worry about the squiggle here. That's just a glycerate ester, which triglyceride. And if we have double bonds here, these are the plant oils, okay? If we start to hydrogenate some of these alkenes, partially hydrogenate to a monounsaturated oil, this is like an olive oil, oleic acid, they begin to become more solid, and margarine, this artificial butter that's been developed, we take plant oils, which are polyunsaturated, and then hydrogenate just some of them. You can go all the way and hydrogenate this last double bond and go to the fully saturated one, which would be stearic acid, which would be a solid at room temperature. Now, these also undergo something called allylic oxidation. So the allylic positions here that are highlighted in blue, and you might have to look that up in your book, make sure you can see that. But there's a problem with unsaturated fats that undergo these hydrogenases. So here's a cis double bond in an unsaturated oil. It might be polyunsaturated with multiple cis double bonds. But every one of these allylic positions are kind of special in that they can react with oxygen just from the air. This is called an auto-oxidation process, and it's part of the process of degrading oils. They can become these peroxides at that position. So you can see it's an oxidation reaction. We're inserting peroxide in this carbon hydrogen bond at the allylic position. Now, I don't have time to go through the mechanism of that. It's known. These allylic peroxides then eventually break down and break carbon-carbon bonds and create aldehydes and other oxidation products, and that's the rancid process that these unsaturated fats can undergo. But if you don't have these double bonds, if you have fully saturated fats like stearic acid or palmitic acid, these guys are much more stable long term on the shelf. So it's kind of a trade-off in the food industry to make more of these saturated fats, which are more shelf stable. They're solids at room temperature generally. Remember, the more double bonds we have here, they tend to be liquids. But the trade-off is here, they can air oxidize and become rancid quite quickly, whereas the saturated fats are very stable. Another thing here, health-wise, if your diet is high in saturated fats, you tend to have more LDLs in the body. And you've probably heard of that acronym before. What does that stand for? Low density lipoprotein particles in the blood. These lower density lipoproteins are transport vesicles for cholesterol and other fats in the body because those aren't water soluble. Remember, the blood is an aqueous solution. So these vesicles are formed within the blood to transport those non-soluble fats. But if they're highly saturated like this, they tend to be the low density ones, which are large. And the problem there is in the small arteries, especially around the heart, those can become blocked. Those atherosclerotic plaques can form blockages around the heart, can lead to heart disease, even heart attack, and other bad things. So LDLs, we try to lower those in the body. There are blood assays to determine these. But if you have higher amounts of unsaturated fats in the body, we have the opposite type of particles. We have the HDLs. And you remember the acronym here, what does this stand for? Same thing for the L, that's lipoprotein, the transport particle. But what does the HD stand for? Higher density. These tend to be smaller, they don't form the plaques as easily, And these are the good forms of cholesterol, it's said. Okay, you have higher amounts of HDLs in your blood tests, you have a better outcome health-wise. If you have higher amounts of LDLs, saturated fats. One other issue. When we have polyunsaturated, the plant oils, linoleic and linoleic acid, and we try to just partially hydrogenate these, we're trying to make them more stable, less double bonds, so less allylic oxidation, more HDLs, and that's all a good thing. But when we partially hydrogenate here, we also create what's called trans fats. Maybe you've heard about those. It's actually an isomerization process around the double bond. The more stable one is actually what? The transalkene. But in nature, from the enzymes, they're made in the cis form. The trans fats have a couple of problems associated with them. They undergo the allylic oxidation more readily. They tend to degrade and go rancid quicker. And they tend to have what? Higher amounts of HDL or LDL? That's right, much higher amounts of LDLs. So those will be raised with the trans fats, and that's a bad outcome health-wise. So a little bit of application here. Sorry to diverge too much there, but your book talks about it a little bit, and I'm just giving you a little more details on that. I think that's enough there. Let's go back to the board here and talk about alkyne hydrogenation. So we have alkynes, which we just have what? Second pi bond. So we can do the hydrogenation there. And if we have an alkyne, say 2-butene, and hydrogen here, and palladium. Remember I said it's hard to measure out just one equivalent. So usually if we show hydrogen H2, we mean excess. And what will occur very quickly is production of the alkane. Okay, so an alkyne to an alkane with the normal catalyst will be made there. So that's typical for all sorts of acetylenes, alkyne materials. But if we have palladium here that has not just showing palladium here, but it shows palladium with calcium carbonate and lead tetraacetate, PB, sorry, diacetate, and quinoline. That's what your book is showing, and that's a lot to write out every time. We're not going to deal with that. If you just say Linlar, palladium, and then just show Linlar, so just the palladium and Linlar, with the hydrogen, you have to have the hydrogen here. You'll stop at the cis alkene, okay? So you'll see the syn addition of the two hydrogens here. Now, we call this a poison catalyst in that there are other groups bonded to the palladium surface, which slows down this second step here. So if we add more hydrogen, and if we add an active catalyst, this would go very quickly, like in the top example. But if we have the poison catalyst, this second reduction here will be very slow. And we can stop it after, a couple hours, whatever. And it'll reliably give us just the cis product, okay? So any type of an alkyne, let's do a more complicated one here. We have this type of thing, and we say palladium, Linlar, and hydrogen. Don't forget the hydrogen, you need that there. But by saying Linlar, what's our product going to be now? It's going to be the cis alkene. Okay? So everything else there is the same, and the two hydrogens came on from the same side, and we stop at the cis. So don't draw the alkane product here when you see Linlar. Hydrogen, it'll stop there. It's a kinetic effect. You've got other groups on the palladium now. The second step here is slow. The alkene itself is a bigger molecule. It's harder to bond to the palladium surface to do that second step. But if you have a regular type of active catalyst, it's easy to coordinate this again and do the over-reduction, okay? So if you say Linlar or show some of this stuff here, we know you need a poison catalyst, and you'll stop at the cis product there, okay? Let's look at the other process here, going to the trans product. Okay, so that's the Lenoir reduction. We sometimes call that the half reduction, or the poison catalyst reduction, going from an alkyne to a cis-alkene. Now, what if we want the trans? So we've got our same 2-butene here, and we want to get the trans product. And the trans product is the more stable thermodynamic product. But we have to use a different reagent to do that. We use sodium metal in ammonia. Okay? Usually this is lower temperature, and ammonia at that temperature will be a liquid, and it's the solvent. It's actually the proton source also. But notice it's doing a half reduction. It's stopping at the alkene, and it is the trans product, the thermodynamic product. Let's see, maybe I'll show you the mechanism. Well, no, let's do a couple other examples. So let's say we've got this guy. If we do sodium ammonia on that alkyne, what do we get? Again, the trans product. Okay. So we can combine this with a couple different things. You know, anytime we have an alkyne, when we do a synthesis project or whatever, we want to go to the alkene that's trans here. We can use the sodium and ammonia. Maybe we'll do the mechanism, just a little bit of it. We need to get on to the other reductions here. The lithium aluminum hydride, and that'll be about it for today. But let's do the mechanism, at least enough of this. Let's take the sodium metal and show its valence electron. Okay, and let's take one electron out of the pi bond here, and let's put the other electron up here, okay? And this electron's going to come off there. And what are we going to get? We're going to get the negative charge here and the one electron there. And that looks kind of funny, but it shows all the electrons and where they're at. And what do we get here? That's a negative charge, a carbanion on this final position. It's going to be unstable, but in the presence of a proton source, ammonia, you know, that's acidic. It's not a great acid, right? The pKa here is 38, but that's a very reactive position here. So this mechanism is definitely a high energy process. So we've got the sodium metal. We still have one electron there, right? And if we take that proton off and protonate our anion there, right there, we get NH2 amide, sodium amide. Well, there it is. That's one way to form that strong base, sodium amide, that we've been using there. But our alkene is reduced. We put one electron in there and we protonated the anion. But what about this? We've got to do it again, right? We've got to have another equivalent of sodium, so it is excess here. And you see, we keep the two alkyl groups across from each other. Now we have a new vinyl anion. Again, that's a high energy thing here. We've got more ammonia. So yeah, you need excess of both the sodium and the ammonia here. And eventually you get to the thermodynamic trans product. Now it's a very different mechanism than hydrogenation of hydrogen gas and palladium, right? This is sodium metal and ammonia, NH3. And it's a high energy process. Sodium metal is a dangerous material. It's difficult to work with, but this is a reliable process to go from what? An alkyne to the trans alkene. So keep in mind that combination of reagents. Questions on that? All right, the last reaction today is going to be reduction of haloalkanes. And this is kind of a different reaction, but it relates to something we've already seen before. Let's take 1-chlorobutane, all right? And let's react it with lithium aluminum hydride. And I like this acronym. It's easier to write out than writing out lithium aluminum hydride. But we'll have to do it for the mechanism. LAH. A lot of hydrogens. Remember, all these reagents we're covering today are reducing agents. You see hydrogens, you see valence electrons available to do reductions. And what's the reduction going to be here? Well, we're going to take off the chloride, when we get the product, we'll get butane. Pretty expensive way to make an alkane. It's not synthetically very useful, but I think mechanistically we can begin to see how this might work. Aluminum with 4 hydrogens on it. What's the charge on aluminum here? That's right, -1. The lithium is there. So how can this reaction work? Well, we need to take off one of these hydrides with its pair of electrons. This is aluminate. It's negatively charged anionic species. It can transfer this hydride, to that carbon and kick off the chloride. This works better with primary. It works with secondary as well. Tertiary, it doesn't work very well. sp2 and sp hybridized alkyl halides also does not work. It also works with bromides and iodides, not with fluorides. Fluorides, carbon-fluorine bonds are too stable. So what are we going to call this type of reaction? Let's see. Here's a good leaving group, right? And I remember I said primary and secondary work. And what are we doing here? We could call this what? A nucleophile. And here's our leaving group. So what type of reaction is it? That's right, SN2. Okay. So it just displaces that from that position and forms a product. So anytime you see an alkyl halide, so this bromide, for example, with LAH, what would it go to? It would go to just simply methyl cyclohexane. Okay. Preparatively, not a very useful reaction, but maybe you've made something else in the molecule and you want to get rid of this halide. Taking it off with the LAH can be okay. We'll learn later with LAH we can reduce carbonyls to alcohols. Again, that's a reduction reaction. You can imagine the hydride going in here. We'll do the details of that mechanism later in 352. There's one more reaction I wanted to show here, and that's reduction of epoxides with LAH. So here we have the same thing. And what is going to be the product? Remember, we have a nucleophilic hydride source here. So maybe we draw it out again. What do we have? Aluminum, negative charge on there. And we've talked about this before. If this is an SN2 type reagent with the alkyl halides, the epoxide is going to act in the same way. So is it going to want to attack at this position, the tertiary position, or this position, the primary position? How many people say the hydride is going to add to the tertiary position? Okay, not very many. How many people say it's going to add to the primary position? Okay, yeah. Isaac says it's going to add here. Okay. Let's go ahead and do that. So again, nucleophile adding at that spot, our intermediate will look like this. We'll now have another methyl there. We'll have O minus. And in this case, we need to quench it with water. So the slash means the same reaction vessel, and we're just dumping in water. We don't dump in water at first, okay? It's only at the end to do what? To add a proton there. So let's go ahead and do that. And what do we get? We get the tertiary alcohol. Where did the hydride add? Well, it was right here. Okay. It opened up the epoxide right there. We did not want to add it here. That would give a primary alcohol, okay, and an isopropyl group there. So it's different than that. So it adds at the less substituted spot, okay? Okay, because it is an SN2-like reaction. Okay, so I think that's enough there. The key reactions from today, I think, are the alkene reductions. The syn addition there, the stereochemistry, gives the cis product if it's cyclic that way. And also the key thing is that LINLAR, the poison catalyst reduction that takes alkynes to the cis alkenes, and then the complementary set of conditions to go from an alkyne to what? The trans double bonds, the trans alkene, using what? Sodium metal and the ammonia catalyst. And then we had a little bonus thing here, I think, with the LAH, with the alkyl halides, and opening the epoxides. So next time, stay tuned. We will do the second part of chapter 12, which will be the oxidations. And we'll see you next time. Very good.